Hey, welcome back to Computer Science Theory. This is COMS W3261, and this is Lecture 8, Part 1, Context-Free Pumping Lemma Examples. Part 2, we will get into Turing machines. So, the teaser for today is, well, it's either going to be easier or harder than the ones we've seen before, depending on your interests. The question is, which actor played Alan Turing in the 2014 film The Imitation Game? So, Alan Turing is a very famous computer scientist. He's one of the fathers of computer science theory, invented a lot of the stuff that we're doing in this class, including the Turing machine. So he's worth knowing. And a bonus question is, who played the cryptologist and codebreaker Joan Clark in the same movie? Also a remarkable cryptologist. I'll pause now in case you're working on that. Answers to the teasers are, of course, Benedict Cumberbatch and Keira Knightley. Announcements for the day. Homework 4 is due on August 26th. That is Monday at 11:59 p.m. Homework 5, the second to last homework with a good chance for extra credit on it, is due on August the 2nd. That is next Monday, also at 11:59. And I also wanted to announce a slight change in video format. So often when I lecture, you've seen me use this purple pen to annotate what I'm doing, to put notes on diagrams. And that's a strategy I do that I think works well in a virtual classroom because it's hard to maintain attention. It's very easy to zone out and do something else and then come back to the lecture and wonder, okay, what was going on before I lost track of this? So it's nice to have all of the notes written down on screen. However, if you're watching this in video format, it's probably not strictly necessary. If you miss something I'm saying, you can go back and listen to me say it again or watch me do it again. So I've taken a suggestion from one of my TAs, and we're going to try as an experiment a version of these lectures where I work a little bit faster and write a little bit less, so things will be more dense. However, I will go back and add the purple notes to the PDF Notability files. So if you're just using those files, you'll be able to see the notes. If you're just watching the videos, you'll be able to hear me say the things that come out as notes. And we'll do this as an experiment. If it works well and we get good feedback on it, then we'll keep doing it. Readings for this week. Section 2.3 discusses the context-free pumping lemma. And then section 3.1 introduces the Turing machine. And decidability, which is, I'll say, recognizability too. Two concepts that we'll talk about later in this lecture. The plan for today is as follows. We'll do a quick review of the ideas behind the enormous proof we saw last time in class. Then we'll do some context-free pumping lemma examples. In the next part, we will introduce the best automaton of all time, the Turing machine. And finally, we will talk about recognizability and decidability. So let's get cracking. So last time, we spent most of our lecture doing a long proof that established that context-free grammars were equivalent in power to push-down automata. So first, we sketched how to convert from a CFG to a push-down automaton. And to do this, we used an automaton that had 3 main states. We labeled these states QStart, QLoop, and QAccept. We began and ended by pushing and popping a $sign from the stack. So that's relatively familiar. That's just a stack marker. And then we also popped one more thing at the beginning. We popped the start symbol for our context-free grammar. And the idea was that the state Q loop would non-deterministically try every possible derivation and then check each of these derivations against the input string, accepting only if one derivation, one complete derivation, matched the input string entirely. So in particular, we had a bunch of rules that copied the rules in the context-free grammar that said, if we have a variable symbol on top of the stack in our PDA, then we can swap it for some string of variables and terminals and push all of them onto the stack. And we also had a bunch of rules that said, if we see a terminal on the top of the stack, we know that terminal is going to appear at the beginning of the final string once the derivation finishes. So we'll just immediately check it against the input. So that's how the derivation would work. We would successively turn variables into strings of variables and terminals and match terminals until there were no terminals left and accept at that point. We also showed how to go in the other direction. So we converted from a PDA to a CFG. And the main idea here was we had variables that looked like APQ. And this variable was supposed to generate all strings that correspond to a computational path from P to Q in our PDA with empty stacks before and after. So we took our PDA, we created a bunch of variables for our context-free grammar, and then we set up rules so that each of these variables could generate all the strings that corresponded to some computational path that took us from P to Q with empty states on each side. We used a couple of simplifications, which let us assume that our main path took us from the start state to the single except state with nothing on the stack before and afterwards. And then we showed how to recursively decompose these variables to make sure they had the properties we wanted. In particular, we saw two cases. We drew pictures like this, which tracked the stack height from some state P to some state Q. One state considered strings that took us on computational paths from P to Q and never emptied the stack entirely. And in that case, we observed that there were states R and S right in the middle of these paths, such that R pushed alpha and that S popped alpha on two input symbols A and B, for example. So that let us substitute this case. It let us substitute the variable APQ for the string of variables in terminals A, ARS, B, where A and B are the input symbols that we read that took us from P to R and from S to Q. So they could be the empty string. We also had a second case. And this was the case in which we went from P to Q with some stack that got completely empty at one or more places in the middle. We called this place R and noted that the string that took us from P to Q was also a string that took us from P to R with an empty stack, concatenated with some string that took us from R to Q with an empty stack. So in this case, we could use the substitution rule APQ to APR, ARQ. And it turned out that these two rules put together, if we applied them to every case and built them up using the transition function, could be used to create a context-free grammar that was exactly equivalent to our pushdown automaton, that generated all strings that our pushdown automaton accepted. So the punchline of this long proof was, of course, that any language is context-free if and only if some push-down automaton recognizes it. We also saw a new pumping lemma. So if you remember, what is the pumping lemma? It's a statement about a class of languages that says any language in this class has a property that it can be pumped. In particular, the context-free pumping lemma tells us that for any context-free language, there is some pumping length such that any string longer than the pumping length, or at least as long as the pumping length, has substrings that can be pumped. And then we are going to proceed today to use that to show by contradiction that some languages are not context-free. So let's write it down again so it's fresh. Theorem. Pumping lemma for context-free languages. So if L is a context-free language, there exists a pumping length P such that for all sufficiently long strings in the language, that is, for all S in the language with S at least P, S can be divided into 5 substrings. S equals U, V, X, Y, Z, such that all 3 of the following conditions hold. The first condition says for all I greater than or equal to 0, U, V to the I, X, Y to the I, Z is in the language. So this is the pumping condition. This says we can repeat V and Y the same number of times, and we'll get a new string in the language. We also have Vy greater than 0. That means one of the strings we pumped has to have some characters. And then finally, Vxy is less than or equal to P. That's equivalent to our original requirement when we were just breaking things down into X, Y, and Z, that XY was not too long. We don't go for too long before we see a repeat if we're thinking about the intuitive proof we did last time. The intuition behind this proof being that, I'll just write this down. If we repeat a variable, we end up getting something we can pump. The proof idea was CFLs have context-free grammars with a finite number of variables, sufficiently long strings, repeat a variable in every derivation, and this loop in derivation, I'm calling it a loop not because our string of variables and terminals is the same when we come back to this variable, but because we come back to the same variable twice, and from there we can take the same rule we took last time, can be pumped. The picture we drew for this intuition was the idea of a big parse tree starting from the start symbol, and partway down the parse tree, some variable R. Partway down the parse tree from R, some other variable. So if we consider S as being the string that gets generated from this parse tree, then we observe we can repeat the subtrees nested under R to get a new parse tree that repeats V and Y. So the intuition was we can have a parse tree that looks just the same, that is, tracks the same rules, except when we reach our second R, we just start making the same choices for rules that we made from our first R. So we'll end up with a parse tree that produces the string UVVXYYZ and shows that that string is in the language. We can nest this. We can do this nesting procedure as many times as we want. And once we do that, we'll end up with UV to the I, X, Y to the I, Z for some string in the language. That was the idea behind the proof we did last time. Just a note, if you are watching this video after watching the in-person lecture last time synchronously, we didn't get to the proof of the context-free pumping lemma in the last in-person lecture. So if you haven't seen that proof yet, it's at the end of the last video. That is the second part of lecture 7 in the YouTube series, just to make sure you see everything we've done if you're going back and forth. However, on the last video, we did not have time to do any examples. So we'll do a couple of examples now of how to use this lemma, and you'll see it's very similar to how we used the original pumping lemma for regular languages. So our first example will be to show that the language B is not context-free. I am going to write out this note because I think it's very important to keep in mind. The CFPL tells us that all context-free languages have a pumping length such that all sufficiently long strings have some decomposition S equals U, V, X, Y, Z that can't be pumped. So thus, to show not context-free, we show any sufficiently long string such that no decomposition can be pumped. That is, the logic here just tells us that we need to find one string that's sufficiently long and in the language, but for that string, we have to show that every possible division into substrings fails. So that's exactly what we'll do. We will, 1, assume that the language B is context-free. 2, thus B satisfies the context-free pump lemma. So B has a pumping length P. For all strings in B that are sufficiently long, S can be divided into U, V, X, Y, Z, such that U, V, I, X, Y, I, Z is in the language for all I greater than or equal to 0. The length of V and Y put together is greater than 0. And finally, VXY has length at most P. So that's what we need to disprove. We need to pick one string, and we need to show that every division fails one of these 3 conditions. So in this case, our language is pretty simple. It's just A to the n, B to the n, C to the n for n greater than or equal to 0. So there's really one most natural string to pick. This is sort of our toy example. So in this case, we'll choose S equals A to the P, B to the P, C to the P. S is in the language, and the length of S is at least P. So we're good there. If our assumption that B is context-free holds, there's some way to divide this string so that it can be pumped. So we will consider all possible decompositions into substrings. And we'll do that by dividing every possible decomposition into two cases, one of which must be true. So case one, let's assume V and Y contain at most one type of symbol each. So V is all A's, or it's all B's, or it's all C's. Same with Y. Thus, as the length of Vy is greater than or equal to 0, that means at most 2 and at least one of the three substrings A to the P, B to the P, and C to the P increases in length in U, V, V, X, Y, Y, Z. In other words, we're doubling V and we're doubling Y. Because we assumed that V and Y contain at most one type of symbol each, at most, we're increasing two of these three strings, and we're increasing at least one of those three strings because one of V and Y must contain some characters. So it follows, therefore, the number of A's, B's, and C's is no longer equal, which implies that U, V squared, X, Y squared, Z is not in B, breaking the first pumping condition of our pumping lemma. Case 2 is at least one of V and Y contains two symbols in I'll say two symbol types just to be clear what I'm talking about. So not exactly two characters, but at least an A and a B, or a B and a C. So two symbol types in A, B, C. Now, pumping V and Y creates a string U, V, V, X, Y, Y, Z that contains some symbols out of order. So for example, suppose I have A, B, 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 well, probably could be equal, C, 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 C. Say this is S, and suppose this is V, and this is Y. Then U, V, V, X, Y, Y, Z equals A, B, B, A, B, 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 C, 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 C. And of course, we have some symbols out of order because we repeated A, B, B twice. So U, V squared, X, Y squared, Z is not in the language. Thus, any division of S fails the context-free pumping lemma conditions, and thus S is not pumpable. B is thus not context-free. So what did we do here? We said, suppose B is context-free, then the pumping lemma must hold. So all sufficiently long strings must satisfy all of these conditions for some division. We chose a sufficiently long string, and then by using two cases, we showed that no division could meet all three of the cases for this string. And here we did use u v squared x y squared z both times, and that was because it was the simplest. But of course, we could use u v0 x y0 z, or u v to the 10th x y to the 10th z if that was more convenient. I just end up using this one a lot because often it's enough to prove a contradiction. We'll do one more example now. And it'll be one that's slightly more complicated or require us to think a little bit differently. In particular, we'll just have to be cleverer about how we choose our string. We'll have lots of possibilities in this case. So second example. Let's let D equal WW such that W is some string over the binary alphabet. So that is, D is any string over the binary alphabet that's some substring repeated twice. We show that D is not context-free. So again, we'll start by assuming for contradiction that D that D is context-free. And therefore, D satisfies the context-free pumping lemma and has a pumping length P. This means that for any string S in the language such that S is sufficiently long, we have S equals U V X Y Z such that U V I X Y I Z is in the language for all I greater than or equal to 0, the pumping condition. At least one of V or Y has some symbols in it, and VXY is at most P. So the third step is to choose a string. Again, this is our hard creative step. And here, it's not quite as obvious. It's not quite as obvious what a good string is, because there are many strings in D and they don't all have the same form. So I wanted to do this example because I wanted to give an example of how you know that your string might not work. You might find some string that is pumpable, and yet some other string would help you complete the proof. So suppose we chose one relatively natural string, 0 to the P, 1, 0 to the P, 1. S is in the language, and it's also longer than the pumping length. So in that case, we're good. However, it's still possible that S can be pumped, right? That doesn't disprove the possibility that D is context-free. We just have to find some S that can't be pumped to prove that. So it could be that most strings are pumpable. And in particular, if our string looks like this, a bunch of zeros, then a 1, then a bunch of zeros, then a 1, and we divide it into u, v, x, y, and z, we do have vy greater than 0, as v and y both contain symbols. They contain a single 0. We also have vxy is no more than p. And finally, we have u v to the I, x, y to the I, z is in the language for all I. The reasoning here is just that if you duplicate v and y, you increase the length of both of the constituent substrings by 1, 0, and you just get, for instance, u v squared x y squared z is just 0 to the p plus 1, 1, 0 to the p plus 1, 1, which is indeed in the language. So the moral here is just, if one string can be pumped, that doesn't necessarily mean that the pumping lemma will always hold, or does hold for the language, I should say. It doesn't mean that every string can be pumped. So we'll try a different string. This one will work. We'll choose s equals 0 to the p, 1 to the p, 0 to the p, 1 to the p. Now, our problem with the first choice of S was that we could pick v and y to capture sort of the same subparts of our two substrings that made up our total string, our two strings of zeros and ones. And then when we pumped v and y, we got more strings that matched. So setting the string of ones to be longer is going to help us prevent this problem. And I'll show you how. So first, as always, we want to note that S is in our language and S is long enough so our conditions should hold. And we'll consider two cases. So we prove that no division of S satisfies our condition by dividing all decompositions into cases. So in particular, case 1, suppose that vxy is a substring of the first 0p, 1p substring of S. So what that looks like is we have a whole bunch of zeros followed by a whole bunch of ones, and then 0 to the p, 1 to the p. So we claim vxy is a substring of that. Now, consider pumping v and y to get u v squared x y squared z. So now I claim so what we'll do is we've inserted another v, And we've inserted another y. So now, as vxy is at most p, we've added at most p characters to this first substring. This means that the midpoint of our string is now a 1. And the reason this is true is because initially we had 0p, 1 to the p, 0 to the p, 1 to the p. If we add some more characters to the first half, we shift the midpoint over. But we can't shift it all the way over to be a 0 unless we add more than p characters. I claim basically whenever we add between 1 and p characters to the first half, which is exactly what we're doing when we pump v and y, the middle character becomes a 1. So now the first half of our string starts with 0, and the second half starts with 1. So u v squared x y squared z does not equal ww for any binary string w. That is, the first half can't equal the second half because the first half starts with 0 and the second half starts with 1. So this defeats case 1. Case 2 is the case in which vxy is a substring of the second 0p, 1p substring of s. And the reasoning here that leads us to a contradiction is the same as case 1. In other words, we pump v and y, we move the midpoint, so the midpoint is now a 0, and that means our first half of the new string is going to end in a 0. Our second half of the new substring is, of course, still going to end in a 1. So the logic is very similar. I won't say same because we do have to flip. We do have to flip the 0s and 1s, but it's very similar to case 1. So you can get it from case 1 pretty easily. Now we have one more case. So we've considered vxy being a substring of the first half and vxy being a substring of the second half. The third case is all decompositions in which vxy straddles the middle. So it's partially in the first half and partially in the second half. So case 3, we'll consider vxy straddles the midpoint of the string. So as a picture, we've got a bunch of 0s, we have a bunch of 1s, then we have a bunch of 0s, then we have a bunch of 1s, and vxy is going to overlap with this middle part, and it's going to have at least some of the 1s on the left and some of the 0s on the right. So first we note that because vxy has linked less than or equal to p, it doesn't include any of the first p zeros or any of the last p1s. So it's just not long enough to include any of this part or any of this part. So now consider pumping down to the string u, no v, x, no y, z, which is just u, v to the 0, x, y to the 0, z, which is 0 to the p, 1 to the I, 0 to the j, 1 to the p, for some I and j. Now, because vxy is less than or equal to p, I and j can't both, sorry, it's not quite the argument I wanted to make. So I and j can't both be p, as this would imply that the length of vxy was 0. Sorry, vy equals 0. So the argument I'm making here is that I've deleted v and y. I know that one of v or y has some symbols in it. That's one of my first 3 assumptions. And I'm saying, well, I and j can't both be p because that would mean my string was unchanged and there was nothing in v or y. So one of I or j must be less than p. However, this implies that 0p, 1 to the I, does not equal 0 to the j, 1 to the p, and thus uxz is not in my language D. So, therefore, no decomposition of S into U, V, X, Y, Z satisfies the pumping lemma. So D is not context-free. Kind of interesting because we've seen this language before as an example of a language that was non-regular. And now it turns out it's not context-free either. We will see an automaton later in this lecture that can recognize this particular language. But it turns out to be a lot tougher than it looks to recognize. So now we'll break until the next video. Next up, we'll get to talk about Turing machines at long last. Thanks for watching. See you in the next one. Bye.